All right, the sixth and final of these videos where I'm proving all these different trig identities. We've already shown the angle addition and subtraction formulas as well as the double angle formulas for sine, cosine, and tangent. In this video, we're going to look at the half angle formulas for sine, cosine, and tangent. And it'll turn out to prove these half angle formulas that I have written in blue. All we need is the cosine double angle formula, which are written out here in red. So remember in the previous video when we talked about double angle formulas, we came up with one for sine and one for tangent and then three different ones for cosine. And you probably think that we'd use sine, cosine, and tangent here for the half angle formulas, but we're not going to. We're only going to use the cosine double angle formula and only these two versions of it down here. The trick I'm going to use over and over again is I'm going to start with one of these formulas. For the first version, I'll use this one. And playing the role of a in this formula, I want to plug in half of a. So if I plug in half of a here and here, on the left side of the equation, I have the cosine of twice half of a. Well, twice half of a is just a. On the left side, I would have the cosine of a. And on the right side, I would have 1 minus 2 times sine squared of a over 2, because again, I'm plugging in a over 2 in place of both of these a's here. Note that what I now have is an equation which has the sine of a over 2 in it. The sine of a over 2 is exactly what I'm looking for. If I could solve this equation for the sine of a over 2, I'd be done. Well, maybe I add this 2 times sine squared a over 2 over to the left-hand side of the equation and subtract cosine of a over to the right side of the equation. Now to get this all by itself, all I gotta do is divide by 2 and take the square root of both sides. There's the division by 2 step. And then remember, when you take the square root of both sides of an equation, you got to put in a plus or minus. So I get the sine of a over 2 is either plus or minus the square root of 1 minus cosine of a over 2. This is a little bit misleading of a formula. It's not implying that the sine of a over 2 has two different values. It's just saying we don't have enough information to know whether it's the positive or the negative of these two values that we want. So when we go and actually use this formula, we'll have to be a little bit careful. There aren't two answers. It's just there's two possible answers and you have to choose which one works. But those are all issues for a different video. In this video, I just wanted to come up with the formula and show how we can use this cosine double angle formula to come up with our sine half angle formula. Almost identical steps will work to come up with the cosine half angle formula, except instead of starting out with this version of the cosine double angle formula, I'm going to start out with this version of the cosine double angle formula. I'm going to again do the trick where I change all the a's into half of a's. So on the left-hand side, I got the cosine of 2 times half of a, which is just a. And on the right side, I got 2 times cosine squared of a over 2 minus 1. Note that just like up here, I have in my expression the cosine of a over 2. If I could just solve for that, I'd be done. Solving for that will be almost identical to how I solved for it up here. First, we'll add the 1 over to the left-hand side of the equation. Then we'll divide by 2. And then we'll take the square root of both sides of the equation and be done. Again, taking the square root, you got to remember to put in the plus or minus. And again, this does not imply that there's two different values for the cosine of half of some angle. It's just that there's two possible values and you'll have to choose which one actually works. Okay, so this cosine double angle formula that involves sines produced my sine half angle formula, and this cosine double angle formula that involved cosines produced my cosine half angle formula. But what am I going to do to come up with my tangent half angle formula? I don't have a cosine double angle formula written in terms of tangent. What am I going to do? Well, the trick that we can do is just recognize that tangent is sine over cosine. So if we know the sine of a over 2 and the cosine of a over 2, it's easy enough to come up with the tangent of a over 2 by just dividing the answers that we got in these previous two proofs. It's kind of a mess to look at, but we can clean it up pretty quickly. The first comment is that when you take the square root of something divided by the square root of something else, that's the exact same as the square root of the quotient of those two things. And what I have is the quotient of two different fractions, which is kind of annoying, but there's this little trick that when you're trying to divide fractions, you can multiply by the reciprocal of the denominator. You can take this one and flip it upside down. If we do both those steps at once, because I'm a little bit lazy, I would have the square root of 1 minus cosine of a over 2 times this upside down, so 2 divided by 1 plus cosine of a. Note that I still have the plus or minus out in front. Well, the good news is these 2's cancel out. That'll get us a little bit closer to our right answer. And I have just 1 minus cosine a divided by 1 plus cosine of a. The bad news is that's not either of the forms that we were hoping to come up with. The two forms we were hoping to come up with don't have radicals in them. They're this, but simplified. How do we get rid of this radical? Well, there's this little trick that you can do. Anytime you have a fraction, you can multiply the top and the bottom of that fraction by whatever you want without changing its value. It's the reason that 1/2 is the same as 50/100ths. So if I felt like it, and it shouldn't be obvious why I feel like it, but if I wanted to, I could multiply the top and the bottom here by the square root of 1 plus cosine of a. Why would you do that? Well, because watch what happens. When I'm multiplying fractions, I multiply straight across. When I multiply the square root of something times the square root of something else, I get the square root of the product of those two things. So in the numerator, all I got to do is figure out what 1 minus cosine of A times 1 plus cosine of A is equal to. If you FOIL, 1 times 1 gives you 1. 1 times cosine of A gives you positive cosine of A, but 1 times negative cosine of A gives you negative cosine of A, and those two cancel out. And then negative cosine of A times positive cosine of A gets you negative cosine squared A. In the denominator, I'm not going to bother foiling things out because what I have is a perfect square. I have 1 plus the cosine of A squared. Okay, so the bottom is going to work out really nicely because I have something squared, and the square root, and formally speaking, will cancel each other out. But what about the top? Well, up top, I got 1 minus cosine squared A. And maybe you recognize that. Maybe you remember from your Pythagorean identity that because sine squared of an angle plus cosine squared of an angle is always equal to 1, if I subtract cosine squared from both sides, I get that sine squared of an angle is 1 minus cosine squared of an angle. So if I'm ever lucky enough to have 1 minus cosine squared of an angle, like I do right here, I can replace that with sine squared of that angle. What I'm saying is I have plus or minus the square root of the sine squared of the angle A divided by 1 plus cosine of A squared. Now the top and the bottom are something squared, and I'm taking the square root of something squared. Those can cancel each other out. And actually something else happens really nice. When you take the square root of something squared, it's not just that they cancel, you get the absolute value of that thing. It can't possibly be negative. So that takes care of this plus or minus as well. The plus and the minus are gone, the squareds are gone, and the square root's gone, and I'm left with just the sine of A divided by 1 plus the cosine of A. That was one of the two forms that I want. What about the other form? Well, we can get there pretty quickly. If you go back to this line where we said that the tangent of half of an angle is 1 minus cosine of the angle over 1 plus cosine of the angle. We were here, and this is where I decided it was a good idea to multiply the top and the bottom by the square root of 1 plus cosine of A. What if I didn't choose the square root of 1 plus cosine of A? What if instead I chose the square root of 1 minus cosine of A? I wonder what would end up happening. Well, let's see, the steps would be pretty similar. I can think about this as the square root of this entire thing, and then I'm taking the square root of something times the square root of something else, so that's just equal to the square root of the product. So all I got to do is figure out what is 1 minus cosine of A times 1 minus cosine of A. Well, I guess that would be 1 minus cosine of A squared. What about down in the denominator? I got 1 plus cosine of A times 1 minus cosine of A. Think FOIL. 1 times 1, 1 times negative cosine, cosine times 1, cosine times negative cosine. I think the cosine and the negative cosine will cancel out, and I'll get 1 minus cosine squared A. Very similar to how I had 1 minus cosine squared A up in the numerator here. And then, just like I did with this 1 minus cosine squared A, I can change it into sine squared A using my Pythagorean identity. And I have the square root of something squared divided by something squared, which is just the square root of some quotient squared. The square and the square root cancel out. If I include an absolute value, which gets rid of this plus or minus, what I'm saying is when all the dust settles, I got 1 minus cosine of A divided by sine of A, the second of the two forms of our tangent half angle formula that I was trying to come up with. And mercifully, that was the last of the formulas that I was hoping to prove in this 6-video sequence, so I'm now done making these videos.